We're in Module 2, and we're talking about confounding variables. To get our minds on confounding variables, let's answer this question. Suppose you would like to investigate the relationship between alcohol consumption and heart disease. What might be other factors that influence either alcohol consumption or heart disease? Here's what we imagine in our ideal world of research. We have a scenario, an intervention, an exposure, and an outcome. Given our original example, that intervention, alcohol consumption, and the outcome, heart disease. Here's what we actually experience. We have the scenario, we have our intervention, exposure, we have our outcome, and then we have confounding variables, the other factors that also affect that outcome. So as you thought through it, what were some of those factors that might affect the outcome of heart disease? Here's my not comprehensive list. I'm sure you came up with more, but some of those confounding variables: age, smoking status, family history, body mass index, socioeconomic status, dietary habits, exercise habits. Not only do those confounders affect heart disease, but they also might affect amount of the exposure, the alcohol intake as well. So our definition of confounding variable is something other than the study variable, the alcohol consumption, which has or could have an impact on the outcome. So confounding factors can distort the true relationship between the study variable and the outcome. One implication is a false negative, where the confounding variable may mask an actual association. So here, because a confounding variable is at play, we don't see the association between the intervention and the outcome, when in actuality there is an association. On the other extreme, or a false positive, we may falsely demonstrate an apparent association. So we falsely see an association between the intervention and the outcome, but it's actually because the confounding variable is at play. And no matter what, these confounding variables can distort the true relationship between the study variable and the outcome. So what do we do about it? At the end of this video, I'll show you a brief video dealing with adjusting confounding variables. First thing to do about dealing with confounders is that each study should identify and be clear about those confounding variables up front. If possible, exclude them within inclusion and exclusion criteria for the study participation. As an example, for excluding those confounders, when we're talking about alcohol consumption and heart disease, we can exclude from the study participation anyone who is an active smoker. So next, we're going to measure and report all potential confounders. So any lab values, diagnostic features, disease severity, PFT values, demographics, and any other known factors that can affect the outcomes. So number 3 here, at the end of your study, you have all the data. Now it's time to analyze that data. This is where our statistics comes into play. And here, using statistics, we control or adjust for our known confounders to more accurately represent the true relationship between the intervention and the outcome and mute those confounding variables. You see both stratification and multivariate regression here. We're going to talk more about statistics later. What you need to know now is those are statistical methods for both controlling or adjusting for known confounders. Number 4 here is just the idea of being fully transparent. Our expectation is that both adjusted and crude values are given and discussed within the study. Also, the potential limitations of the study caused by the confounders. So confounding variables need to be reported in a study. One way you see them reported is through baseline characteristics, which is the table you're seeing here. These are the characteristics of the subjects at enrollment. This study is evaluating survival rates for ARDS patients with ECMO versus the control group. The 3 columns, the first is a confounding variable characteristic. The next 2, the ECMO group and the control group, are for the 2 study groups. And then as you go down, we're looking at age, sex, immunocompromised condition, SOFA score, medium time since intubation, cause of ARDS, and on and on. And as we take a quick glance, we can look from one column to the next and see if there are any that have glaring differences. You can see at the age, there's about a 3-year difference from the ECMO to the control group, and you can ask yourself, is that 3-year difference going to affect outcome? Do they do something? Do they adjust for it? Evaluate going down. I am asking myself, are any of these values significantly different from the other, from the ECMO group to the control group? And the one that does stand out for me that I would keep in the back of my mind is at the end, second to the end, the recruitment maneuvers, significantly more in the control group. So again, a baseline characteristic table is a way to report our confounding variables and is the characteristics of the subjects at enrollment. Here's a brief video on adjustments and how to communicate adjustment by Professor David Spiegelhalter from the University of Cambridge, the Winton Center.
Studies often report estimates of odds ratios or hazard ratios that have been adjusted for factors such as age, sex, and so on. But what does this mean? And how can we communicate it without using jargon? Well, suppose we take a group of individuals and measure their height and weight and plot them in a scatter plot like this. We can see there's actually quite a strong relationship between the two. But we know that biological sex influences someone's height and their weight. And so we should really look at this relationship in men and women separately. When we do that, plotting the men in green and the women in orange, we find out that there's still a relationship between height and weight in men, and there's still a relationship between height and weight in women. But this relationship is a lot less strong as it was overall. What we say is that this is the relationship adjusted for sex. In other words, keeping sex fixed. This was an extremely simple example that only adjusted for one factor. But in practice, studies tend to adjust for a whole list of factors simultaneously. Let's look at a more complex example. Suppose we want to investigate the relationship between exercise and heart disease. But we know that someone's age might influence the amount of exercise they do and also their risk of heart disease. So unless we take age into account, it could interfere in our understanding of this direct relationship. Because of that interference, age is known as a potential confounder. Other confounders could be smoking, diet, and socioeconomic status. Now, these may not directly cause changes in exercise or heart disease, but they are linked to these factors, both the risk factor and the outcome that we're interested in. So what we really want to do is estimate this relationship while keeping these confounding factors fixed. So how do we do that? Well, We have to collect data on all these factors on a group of individuals, and then use a statistical method called regression analysis. And this allows us to estimate the relationship between two variables, such as exercise and heart disease, while keeping these other confounding variables fixed. And this is what is known as adjustment. But it's important to remember that adjustment is always inadequate. There may be confounders that we just haven't measured. For example, we might not know smoking status. Also, there may be confounders that are measured imprecisely. We can ask people what they eat, but it may not be very accurate. And then there may be measures like socioeconomic status that are very precise categories, but in fact are very rough summaries of a much vaguer idea of social circumstances. And finally, there may be, in fact there always are, variables down here that are linked to heart disease and exercise, but that we just don't know about. We haven't measured them. And these have got the wonderful name of lurking variables. For all its limitations, adjustment is still an essential technique for handling observational data. But even if you have adjusted an estimate for a long list of factors, you still have to be very cautious about how it's reported, and you cannot claim a causal relationship. Now, let's look at some phrases you might use to communicate adjustment. Suppose you want to report an estimate of the link between A and B, say exercise and heart disease, after adjusting for age, smoking, diet, and so on. Now that's fairly technical language, and for less sophisticated audiences, you might want to say after controlling for a list of factors, or keeping this list of factors fixed. Rather more loose, but still very reasonable, is to say taking into account age, smoking, diet, and so on. So, adjustment is a tricky concept, but it's extremely valuable. And these phrases should help you communicate the gist of the idea.